So, in this lecture, we are going to start discussion on diffraction of X-rays from crystals. In the last lecture, we looked at diffraction in which the grating that was used was a DVD, and we had used a green laser as our specific with a specific wavelength to show diffraction. Now, in crystals it is a similar thing. Now, we have a three-dimensional grating in which each atom in a crystal is a scattering center. Now, but here we cannot use something that we use for the DVD like the green laser, because the wavelength of the green laser is, or for that matter any visible light, is much more than the spacing between atoms. For example, if I look at, let us say, the following cubic crystals, and we look at the lattice parameter A. Now, let us take copper, its lattice is FCC, the lattice parameter is 0.362 nanometers, or in another unit it could be written as 3.62 angstroms. Now, generally we will prefer to use the nanometer unit rather than the angstroms unit. Diamond, again it is an FCC lattice and its lattice parameter is 0.357 nanometers. Consider silicon, again FCC, its lattice parameter is 0.343 nanometers. Consider iron, which is a body centered cubic crystal, we have 0.294 nanometers. Finally, if I look at molybdenum, BCC, 0.315 nanometers. In each case, the lattice parameter, therefore the spacing as well between atoms, is much smaller than the wavelength of green laser. Now, for diffraction to occur, the beam that is being used has to be of a similar order of magnitude, the wavelength of that beam should be of similar order of magnitude as the spacing between atoms, and that is why we use X-rays. Now, typically wavelength of X-rays, lambda, varies between 0.1 nanometers, or one can write 1 angstroms, to about 1 nanometer, that is about 10 angstroms. So, you can very clearly see that X-rays is going to have the right wavelength to be able to get diffraction from a crystal. Now, just before we start talking about X-ray diffraction, let me say a little bit about production of X-rays. How are X-rays produced? Well, essentially we bombard target metal. So, this is a metal target. We bombard this metal target with high energy electrons. That results in the production of X-rays. Now, what is the mechanics behind it? Well, first of all, when the electrons hit the metal target, there will be a rapid deceleration of the electrons and their energy will get converted into various radiations, and big chunk of them, that radiation would be in the basically the X-ray wavelength. So, rapid deceleration produces X-rays. So, for instance, if this metal target was, let us say, molybdenum, and then if I look at what kind of a spectrum I will get when I target electrons onto the molybdenum target, well, we might get something like this is 1 angstrom, 2 angstroms, 3 angstroms, and we might get, and this vertical axis is the intensity of X-rays that is produced. We might get something like this, perhaps at an accelerating voltage of 20 kilovolts. So, when the electrons are accelerated through 20 kilovolts, we might get a spectrum of wavelengths. Now, if I increase this accelerating potential to, let us say, 25 kilovolts, then we get some interesting effects. This could be at 25 kilovolts. This is really not drawn to scale, but let me just shift this a bit. Maybe out here is about 1 angstrom. So, when I increase the potential from 20 kilovolts to 25 kilovolts, we start getting what is called as characteristic radiation. And these characteristic radiation have a very specific wavelength, which is a signature of the target metal that we are using. Now, what is this characteristic radiation? Let us just look at it. Let us say this is the nucleus of an atom. Then I have the K shell, I have the L shell, and let us say the M shell. Now, suppose electron hitting this, so this is the nucleus of a atom of a target material. An electron ejects, collides with an electron in the K shell and ejects it out. This will take the atom into a higher energy state, and it can recover back by an electron jumping from the L shell to the K shell. And as a result, there will be emitted radiation, which is a characteristic radiation. It could also happen that an electron from the M shell may jump into the vacant site on the K shell. Then that will also result in a characteristic radiation. So, an electron jumping from the K shell to M shell produces what is called as K beta radiation, and jumping from L shell to K shell is what is called as K alpha. And if I go back to the spectrum, then this is K beta and this one is K alpha. Normally, we use the K alpha characteristic radiation when we want to do an experiment with a monochromatic X-rays, which means that X-rays of a specific wavelength. So, how to get a specific wavelength, then we use filters. So, filters are used to filter out what is called as the white radiation. So, white radiation is filtered out and only the characteristic radiation is left. This can be used for conducting X-ray diffraction experiment. There are also techniques in which we do need the white radiation, then we will use the white radiation as is. But I will not get into the theory of filters in this course, it is beyond the scope for this course. So, we just assume that either we have a white radiation or we have a characteristic radiation and we can work and do X-ray diffraction experiments. Now, we will get into the theory of X-ray diffraction, starting with scattering of X-rays from atoms. Now, I have a crystal where there are atoms at specific locations and when an incoming X-ray beam hits the crystal, the X-ray photons will be hitting individual atoms, and as a result each atom will scatter X-rays in all directions in a kind of, you can imagine, in a spherical way. So, each atom is scattering X-rays in different directions. The intensity may vary depending on the direction, but all atoms will scatter X-rays in the manner that I am drawing this. So, I can write that atoms scatter X-rays in all directions in 3-dimensional space. Now, using these ideas, let us come to the famous Bragg equation. Bragg equation, or also referred to as Bragg's law. Now, here imagine now we have atomic planes. I have an incident beam. So, these are my atomic planes. I have an incident beam of X-rays. Let us say it gets scattered by this particular atom in some direction, and similarly it will get the other atoms on the same plane will also be scattering X-rays in different directions, but we are looking at some specific direction. We can consider the second row of atoms. The beam hits this and it gets scattered in this manner. So, I have essentially this is my X-rays. Let me call this as, let us say, ray 1, this is ray 2, and I have a point Q where I have the detector of X-rays. Now, I have, so as I said, when the X-rays hit the atoms, the X-rays are going to get scattered in all directions, but we just look at a very specific direction and then examine what what kind of an intensity we will get in that direction, and particularly we will choose a direction such that, let us say, this is the incident beam angle theta. So, the diffracted beam or the scattered beam will look in a direction which is also at an angle of theta. So, it looks like as if it is a reflection, but it is not a reflection. Please make a note of it, it is a scattering process, and we want to find out what is the resultant wave at the point Q, whether there is going to be constructive interference or destructive interference, as I had discussed in the last lecture. We can do the following construction now. Let me drop a perpendicular, let us say I will call this as point A and this point as B. So, I am dropping a perpendicular from point A onto ray 1 or ray 2, and from the same point I am also dropping another perpendicular onto ray 2 from point A. So, let me call this as point C and this particular point as D. You can clearly see that ray 1 and ray 2 would have travelled a different distance when they reach the detector at point Q, and hence there is a path difference. Now, what is the path difference for these two rays 1 and 2? So, path difference delta would be equal to BD plus BC. See, BD and BC are the extra distance that ray 2 has travelled as compared to ray 1. Therefore, the path difference between the two rays 1 and 2 would be BD plus BC. Now, let us say that the interplanar spacing of these planes, atomic planes, is D. Hence, very clearly from the triangle ABD and ABC, so triangles ABD and ABC, so this is from triangles, we can write that BD is equal to BC is equal to, well, let us see, if you give a careful thought, these two angles would also be theta, and hence BD would be equal to BC would be equal to D sin theta. So, therefore, the path difference simply is 2D sin theta. Now, from the previous lecture, we know that we would have constructive interference if the path difference delta is an integral multiple of wavelength. Therefore, to get diffraction in the direction at point Q, we can then write, replacing the path difference delta by n lambda, in this equation, we can write n lambda equals 2d sin theta. Now, this is the Bragg equation, which you perhaps would be very familiar with. Now, let us take another look at the Bragg equation now. So, my Bragg equation is n lambda is equal to 2d sin theta. So, n is called as the order of reflection. So, n will take up basically integer values like 1, 2, 3. So, if n is equal to 1, it is a first order diffraction. If n is equal to 2, it is a second order diffraction. And lot of times I should also point out that the terms diffraction and reflection are interchangeably used simply because of the geometry that we have made in deriving the Bragg equation, where the incident beam angle is the same as the diffracted beam angle, as if there is a reflection, but it is not really a reflection, but this is commonly used term that we get a reflection whenever we get the Bragg equation is satisfied. So, now it is for convenience we can try to eliminate n from this equation, and how we can eliminate n is as follows. Lambda can be written as 2d upon n sin theta. Now, let us try to understand this term d upon n. Now, d is the interplanar spacing, as I had mentioned, interplanar spacing of some atomic planes, which we can denote it by the indices HKL. So, these are basically a set of parallel HKL planes. Now, if you go back to the early lectures when we had started crystallography or the crystal symmetry part of this course, I had mentioned that if d is the interplanar spacing of HKL plane, then d upon n is the interplanar spacing of NH, NK, NL planes. You can go back to those early lectures to review it, that we had arrived at this conclusion. And hence, what I can do is, maybe I can replace this and write it as d prime, that d prime becomes an interplanar spacing of NH, NK, NL plane. And hence, the Bragg equation could be written as 2 d prime sin theta. Well, I can also remove the d prime part and I simply write it as 2d sin theta. Now, let us try and understand this, and very often you will find that this is the Bragg equation that we typically use. Here, let us take an example. Let me consider diffraction from a unit cell well, let us say I have just atoms at the only at the corners. So, my scattering centers are at the corners, and let us say I am looking at these planes. These are nothing but 0, 0, 1 set of parallel planes, where this is my reference axis. It could be cubic, it may be non-cubic, it does not matter. Now, you can consider first order reflection, which means n is equal to 1. Now, consider second order reflection, which means n is equal to 2 from the set of planes. So, reflection from 0 0 1, here second order from 0 0 1. Now, instead of considering second order, what I can do is consider first order from, what do? I multiply n into the indices and I will get n is equal to 2, I multiply it into 0 0 1 would give me 0 0 2 planes. Now, what are the 0 0 2 planes? Well, 0 0 2 planes are these set of parallel planes 0 0 2. So, therefore, writing in this form, we consider everything as first order reflection, and it is basically just for convenience of calculations, because even though I had said the scattering centers are only at the corners, and now I have put a middle plane which have no atoms, this is a non-atomic plane, there will be no scattering from there. So, it is essentially for mathematical convenience. So, with this I conclude this lecture, and in the next lecture we will look at scattering in some bit more detail with the idea of developing how the intensity of X-rays vary or controlled by when there can be different distribution of atoms, different kind of atoms. The atoms need not be only at the corners, the atoms are going to be in other locations as well, depending on the kind of motif that we put into the crystal and so on. Thank you.